All right, we've looked at how to determine limits from a graph, and we've learned how to determine limits by exploring numerically. But both of those are sort of inaccurate techniques, and we really want to have a more sophisticated way of determining limits. Now, we made a point of arguing in the previous section that the limit as x approaches a value is not necessarily the same as the function value that the value that the function takes on at that point, but in a lot of cases it will be. And we have some theorems set up in the next section here that will help us deal with some very common and well-behaved familiar functions. This first function we're looking at over here, the limit as x approaches c of the function b, right? We're really thinking about f of x equals b, which is a constant function, right? This is the function that always spits out the answer b no matter what its input is. So does it really matter what x is approaching? No, the answer is always going to be b. Right? So for example, if we look over here at this first example, the limit as x approaches 5 of 3, right, the answer is just going to be 3. So anytime you take the limit of a constant function, you just get that constant function no matter what value c has, right? No matter what x is approaching, the function is always going to spit out the same value. Okay? Now we're going to start to look at some other functions in this second example here. Right? We're talking about the function x. As x approaches c, we would expect x to approach c. Right? This is the identity function. Anytime, right, we're thinking about here the function f of x equals x, right? You put 3 in, you get 3 out. You put 2 in, you get 2 out. You put 5 in, you get 5 out. So the limit as x approaches 2 or 3 or 5 is just going to be that same value. So if we look at our next example, the limit as x approaches 5 of x, we would expect the answer to be 5. Okay. Now, you could try to argue that these aren't the same, and we haven't officially proven these theorems, but they can be proven. They are theorems that we are being given and allowed to use. Theorem is something that has been proven to be true. We can use it, but there are proofs behind all of these theorems. If you are so inclined, you could look at them in the textbook, or I'm sure there's plenty of proofs out there you could find online. But we're going to focus on how to use these limits and start to get us some, basic comfort level with how we determine limits. For this next function, we're looking at the exponential function. Well, not the exponential function, sorry, a polynomial function, right, involving an exponent. Exponential functions have the variable up in the exponent. So here the variable is in the base. But if you were to raise x to a power, like x squared or x cubed or x to the fourth, we could just raise that c to that power. The same way that if c goes into x, c comes out of the function. If c goes into x, then c to the n will come out of this function because that x value is being raised to the nth power. So for this third example, if we wanted to take the limit as x approaches 5 of x squared, we would expect that to be 5 squared, which is 25. Yeah. So individually, right, we know now that the limit of a constant is a constant. We know the limit of x is going to be whatever the x is approaching, that's c value. And if we take the limit of a monomial polynomial with one variable, x to the n, then we know that the answer for that limit as x approaches c should be c to the n. Right. There's another theorem in the chapter, right, that focuses on a couple things. So suppose we already know the limit of a function f of x is L, uppercase L, and we know that the function of the limit of another function g of x is uppercase K. We'll just say L and K for here. Now we're going to make a few basic assumptions that b and c can be any real numbers. We're going to assume that n has to be a positive integer. But if we know the limits of f of x and g of x as x approaches c, then we should be able to put these functions together in all the ways that we've put functions together before. So for this first property, scalar multiple, the limit as x approaches c of a constant times a function, right? If we multiply the function by a constant, we should be able to just multiply the limit by the constant. In the second example, second property, right, if we're going to add or subtract, right, the two functions, we should be able to add or subtract the two limits. Okay. Our next two involve products and quotients, right? In a similar vein, if you multiply or divide any two functions and want to determine its limit, you can just multiply or divide any those two limit values, provided that the limit of the denominator is not 0. If you wanted to raise a function to a power, then you could take the limit of that function and raise that limit to the power. So pretty soon we're going to be able to simplify the limit process here for many of the functions that we become familiar with. And we'll find out that in most cases, the limit does agree with the function value, and we don't have to go through the whole process of approximating or looking at values close to the c value. We can just let the function take on that c value, because most of the functions we've studied, right, the function is exactly where we expect it to be. Now, the way we could use these theorems to solve something like this, right, 4x squared plus 3, the limit as x approaches 2, is to first try to figure out what properties we could use. And notice that on its core level, this is really a summation. So we can say this is the limit as x approaches 2 of 4x squared plus, right, the limit as x approaches 2 of 3. Okay. Now, this second one over here, right, that fits one of the properties we had on the previous slide. So we're good there. We know that that limit is going to be 3. Right? But when we look at this first one here, right, we'll notice that there's a scalar multiple. So we can use the scalar multiple property that says, well, if you're going to take the limit of a function 4x squared, then we can take 4 times the limit of x squared. Right? Now, we already said that the limit of any constant function is just going to be the constant, right? And then again, on the previous slide, right, we had the fact that the limit as x approaches 2 of x squared is just going to be 2 squared, right? So we have 4 times 2 squared plus 3, right, which is going to equal 16 plus 3, which is 19. Okay. Now, off to the side, if we take a look at the original function we were given, 4x squared plus 3, and we determine f of, sorry, not 3, but 2, right? We're going to get the same exact thing we just did. Right? And we shouldn't find this surprising, right? Because polynomial functions, as we may remember, right, x squared, x cubed, x to the 4th, right, and all the other variations, there's no irregular things happening at any points. The function is exactly where we expect it to be. And we have a few nice theorems that deal with some of the familiar functions we're used to working with, right? If we're going to take the limit of a polynomial or rational function, right, the limit of a polynomial is just the value of the polynomial at the c that you're taking the limit as x is approaching, right? So if x is approaching c, you can just plug that c value into the polynomial. Similarly, with the rational function, this is a big provided by here, big situation. As long as the denominator at c is not 0, then the limit as x approaches c of r of x is just going to be r of c, right? It's going to be the top polynomial at c and the bottom polynomial at c. Now, we're going to deal with actually quite a few cases where the denominator is 0, and then we won't be able to simply do this, but we'll have some workarounds for that as well. And also, radical functions behave in a similar fashion. If you wanted to take the limit as x approaches c of the root of x as the nth root of x, then you can just take the nth root of c. So if you want at the beginning, you can start to think about all the properties that it would take to work these problems out. You could think about splitting this into 3 separate limits, this limit minus this limit plus this limit. And if you find it easier to stay organized that way, you could certainly do that. But what we've also learned is that we can probably combine a bunch of those steps into one function. So I'll try this. I'll start this one, right, as 3 separate limits, right? We have the limit as x approaches 1 of 3x to the 4th minus, right, the limit, sorry, I was going a little script there, as x approaches 1 of the square root of x plus the limit as x approaches 1 of 2, right? And then you can further break this down like we did before, the limit as x approaches 1. Take the 3 out, right? And then this one we have a theorem for that says we could just take the square root of 1, and this one we know is just going to be 2 because it's a constant, and then we can take 3 times 1 to the 4th minus, well, the square root of 1 is just 1, and then we follow the order of operations here and ultimately get a limit of 4. But, you know, at this point, once we understand how all these limit properties from our theorems are going to work together, there's no reason we can't just plug the 1 in, right? Because all we're doing is evaluating each of these functions independently and then putting them together appropriately, and we'll come up with the same answer, 4. Okay, so when we go to do one like this second one here, it's a rational function. Let's make sure that negative 2 plus 1 is not equal to 0, right? Negative 2 plus 1 is negative 1, which is not equal to 0. So we're allowed to use the theorem we had on the previous page about rational functions. So we can put negative 2 into the numerator. We can put negative 2 into the denominator. 4 minus 3 is 1. Right? Negative 2 plus 1 is negative 1. So we're going to get as an answer negative 1. Oops, that's not a very good circle there. Okay. So what we're starting to see is that many of the well-behaved functions that we've studied, right, as long as they don't have things like vertical asymptotes or disconnected points or piecewise defined functions, most of our well-behaved functions, there's no reason to think that the limit wouldn't agree with the function value. Turns out to also be true for for trigonometric and exponential functions. These are often grouped together as called transcendental functions. Now, property 7 here, we're going to mostly deal, when we deal with exponentials, we're going to mostly deal with e to the x. All right, let me see, my screen is not writing perfectly here. Let's see if we can do that again. The limit as x approaches c of e to the x. Equals e to the c. Okay, so it does say it's generalized for a to the x. 8 could actually be generalized for log base a, but we're going to just stick with this as logarithms. So essentially all these functions, now for tangent, right, if we think about the graph of tangent, tangent is really sine over cosine, and anytime the cosine is 0, the tangent is undefined, and then we have a problem. But as long as c is in the domain of the given transcendental function, this will behave just like polynomials. So let's take a couple examples like this, right? Having the 3 here is really just a scalar multiple, and we could think about it being outside, right? But we also know that we can just take the limit, the sine of pi over 2 is 1, right? And the answer would just be 3. Make sure that the denominator is not 0. So it's not, right? 3 pi is not 0. So this becomes the sine of pi, right, over 3 pi, which is going to be 0 over 3 pi, which is just 0. Okay. So it's going to turn out that a lot of functions that we want to look at, the limit of the function is just going to be the same as the value of the function. But that's not always the case, and some of the functions that have been sort of skipped over or taught as exceptions to the rule, we're going to deal with those more this semester. So we're going to take a look in the next video at what to do when we don't have a situation where the function and the limit agree, or the function isn't defined at the particular value in question. So as a quick example, just looking ahead, thinking about a function like this, the limit as x approaches 3 of x squared minus 9 equals 3. Well, if we try to let x equal 3, the bottom is going to be 0, right? And the top is going to be 0 as well. And that's going to cause a problem for us when we try to evaluate this limit. So that's what we're going to be dealing with next. But first, it's a good idea to just practice a bunch of these functions where the theorems and properties do apply, like we were looking at here, right? Transcendental functions, rational functions, polynomials, sums, differences, right? Constant multiples, and properties like this.